Okay, so in this we're going to see how we use this thing, our periodic table, to help us make inferences or make decisions about elements we might not have met before. So for that we need to understand some key parts of our periodic table. The first one is, even though we often see hydrogen put here, I'm going to get rid of it because it isn't part of that group or family. I'm going to put it in the middle here, sitting on its own because it's special. All right, so hydrogen, you'll often see here, it's only because it makes the same ion charge as the ones underneath it, but it has nothing else in common with them. For example, hydrogen doesn't react with water. It exists as a molecule. So therefore, it doesn't really belong here. So moving that away is the first thing that helps us. Now, if I was to be asked a question about an element that was, say, down here, and I've never met it before, so let's say polonium, I would be looking at what is next to it and what is above it and below it and see if I know anything about those, because there are trends within the periodic table that help us infer what polonium, for example, has as its properties, particularly because we're doing chemistry, its chemical properties. So the type of bonding that it has, if it makes an ion, what charge that ion might be, that sort of thing. So you might be asked to make those inferences in a question, or have to use that to work out the ion of something when writing its formula. So the first thing that we look at is we actually look at which column the element exists in. And we're going to ignore this middle area here called the transition metals, because they do funny things because of a thing called the d orbital. You'll learn about d orbitals in depth next year, so I'm not going to do anything more than mention them. For these ones, you kind of just need to memorize their key properties for this year. It becomes a bit easier, ironically, next year when you have the d orbital explained. So these columns are called groups or families. Oops, spelling nearly went terrible there. What do they have in common? Well, the main thing that they have in common for chemistry is the number of valence electrons. What do I mean by valence electrons? When we have an atom, like I'll use sodium as an example, sodium is number 11. Being number 11, it means it has 11 protons in its nucleus. And being number 23, it has 23 minus 11 is 12. 12 neutrons gluing that together so it doesn't collapse or fall apart. Then, because it has 11 protons and atoms are electrically neutral, they're not necessarily stable, but they're electrically neutral, then it has 11 negative charges, which are its electrons arranged around that. And its first energy level, or shell, this is nowhere near to scale, by the way, it will have two of those electrons. This electron shell or energy level is too small to take any more than 2. So then the next lot of electrons go around that. And again, this is simplistic, I'm not orbiting in circles. But the cool thing is you learn more about that in year 13, about their orbital shapes. And yes, I'm pairing them on purpose, again, to help you with next year. Once that has 8 in it, it can't take any more. I've still got 1 left over, so it's going to go in a third energy level, a third shell. Because it only has that 1 electron on the outside, this helps explain its chemical properties. Lithium is in the same boat. It only has 2 and then 1. Potassium has 2, 8, 8 and then 1. So that outer shell is where the valence electron or electrons live. It's the ones in the outer shell. And it tells us basically what its valency will be, whether it will gain or lose electrons and how many that will be. So sodium has a valency of 1 because it will readily lose this electron to something else that would prefer to have it, have a stronger drive to have that electron than it has, to make it stable, the sodium ion. So the groups and families have the same number of electrons. Therefore, you would infer they have the same type of bonding. So if sodium is a metal, metallic bonds, everything above it and below it should be a metal. If sodium reacts with, say, chlorine or oxygen or water to make hydroxide ions and sodium ions, then you'd expect it to make something that's an ionic compound. Lithium does the same thing, so does potassium. So we can look at the same types of reactions. So this is why we often call it a family, because it's got similarities. For those who love their biology, the genes, as it were, are very similar. Well, the genes of an atom are its nucleus and its electron configuration. They are the instructions that code for the properties. Across, we see something quite different. So when we go across, and again, I'm going to skip the transition metals because they do funny things. When we go across, we've got what's called a period. I'm hoping this isn't going to go too low on the board. In periods, basically, all we're looking at is a trend there. So we're looking at trends. Going from metal to non-metal. We have going from solid to gas, that sort of thing. The periods have the same number of electron, and we use shells this year, but I prefer the word energy level. So they have so hydrogen and helium only have one electron shell or energy level. Their chemical reactions can be determined, and their differences in chemical reactions can be determined on how full or empty that second shell is. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon all have 2 energy levels, and their valence electrons are all in the second energy level, second electron shell. So therefore, we can explain their differences in chemical properties by how full or empty that valence shell is compared to each other. So this is how we can use a periodic table as a really simple cheat sheet. From our groups and families, we're able to work out things like ionic charge. So for example, if all of these have got 1 electron in their outer shell, they'll lose 1 electron and become +1 ions. 2 in theirs becomes +2. These will have to just remember, I'm sorry to say, at the moment, +3 over here. Then, because these have got a half-filled shell, carbon is our prime example, silicon is another one, no ions. Instead, they do covalent bonding because it takes too much energy to lose or gain 4 electrons, but sharing electrons with other elements works. And then after that, we get into the non-metals that can either be ions or can covalently bond. So we have to look at them being -3, but they can also be covalent, -2 and -1. Again, these can also be covalent. So terrible parenthesis, let's do that again. So what that allows us to do is when we look at our periodic table, if we don't know the properties of an element, whether we should or shouldn't know it, what do I know about what's above it or below it or next to it? If I know a bit about it, then I can infer something. So if I have an element that I need to know that's down here, I can infer that it makes a -1 ion and possibly can also make covalent bonds. I could infer that because it's below iodine, it's a solid. That sort of thing. I could go, oh, it's in the 6th, let's say it's in the 6th period, it'll have 6 electron shells. So I can actually infer a lot without having to remember anything. because I'm given a periodic table, I just have to know how to use it. So that's ambiguous. So first period has 1, second has 1 and 2, third has 1, 2 and 3. So as you go across a period, all of those atoms in that same period have the same number of electron shells as each other. But no, if I go to the next period down, it has an extra electron shell.
Yeah.
So I'll clarify that, thank you, within the same period.
So that number 1 period has 1 cell and 2.
Spot on, exactly. And really, for what you need to be able to do this year, for anything you haven't met before or can't remember something about, that is all you need to get out of the periodic table.